Video 5 here for chapter 6 is a continuation of 6.4 because we have some more considerations to think about for our electron configurations, and then we'll see how these tie into some definitions from earlier in the semester with regard to the periodic table. We left off the previous video with a discussion of abbreviated electron configurations. And to make an abbreviated electron configuration, all you do is take all of the core electrons that you've identified and replace them with whatever noble gas they represent. So here we see a couple of examples of abbreviated electron configurations for lithium, sodium, potassium, and then beryllium, magnesium, and calcium, some group 1 and group 2 ions. And earlier in the semester, we said that the groups on the periodic table, right, the columns, identify things that react similarly to one another. And here we see why, right? Abbreviated electron configurations are convenient to use because they show how similar the electron configurations are for things that are in the same group. All right, we see everything in group 1 ends with an S1. Everything in group 2 ends with an S2. So they like to bond similarly to one another. Right? And that controls where they appear in the periodic table. We see continuations here for everything else. S1, S2, over here, P1, P2, P3s, etc. Right? That's a nice convenient representation of the outer shell configuration, right? Just showing our valence electrons. Again, taking the core and replacing it with a noble gas. A quick tip here, if you're trying to quickly identify whatever noble gas you should be using in your abbreviated electron configuration, right? Identify what atom you're trying to write the electron configuration for, right? Let's say we were trying to use tellurium right here, number 52, okay? And then you identify the noble gas, right, with the highest atomic number without going over the atomic number of whatever you're working with. Okay, so here for tellurium, the closest noble gas is xenon over here, but that has an atomic number of 54, which has exceeded 52, right? So for tellurium, right, 52, I would have to use krypton. That's the highest number I can get, 36, without going over 52. Okay, just a quick way to identify. So if I was doing tellurium, abbreviated electron configuration, I start with krypton and then write everything that's left for those remaining electrons. A couple other considerations, right? And these are mentioned on the periodic table video, right? When you start working with the transition metals, right? So scandium at atomic number 21 and everything after that, we have the D subshell to consider, right? And this is why reading the periodic table like a book with our electron configurations is helpful, because you have to pay attention to that transition. Right? The D subshell can fill with up to 10 electrons because it has 5 orbitals within the subshell. Right? And after we have filled those 10 electrons, then we go to the P subshell. Right? So we go from the 4s to the 3d to the 4p, the 5s down to the 4d to the 5p, etc. We also have to consider later on in the periodic table, right, the F subshell, anytime we're looking at some inner transition metals, so some lanthanides or some actinides. Okay. And in the F subshell, right, there's 7 orbitals, so we can hold up to 14 electrons. So down at the bottom of the periodic table, right, when you start jumping around into those F subshells, you would have to think about going there with some other considerations, the D electrons, okay? Now, for the quiz that is online following this chapter for the spring 20 semester, nothing in the F subshell will be on the quiz, okay? But you are responsible for the S, the P, and the D subshells. There are a couple of exceptions to look out for as well, okay? And I do expect you to know these that are listed here on slide 86, okay? I had you in the periodic table video put a star over the columns for chromium and copper, okay? Because those subshells are where, or sorry, those columns, those groups are where we see our exceptions. And that's because there's some stability, meaning lower in energy, that's associated with having a subshell that's exactly 50% okay, half filled, or completely 100% filled. Okay, so we sometimes see some electrons moving around to help achieve that stability. For example, right, if we didn't know any better, for copper, we would expect it to be argon, right, looking at an abbreviated electron configuration here, 4s2 3d9. Okay, but notice this is 100% filled because S can only hold 2, but D9, that's not great. But if I shift an electron from the S to the D, right, now I go to 4s1 3d10. And then I've got a combination of 50% filled and 100% filled. It's more stable. So everything in that copper row you see go to S1D10. So know that exception. We see the same thing with chromium. Instead of being 4s2 3d4, we move an electron over, and then I get 4s1 3d5, where they are both exactly 50% filled. And it's more stable that way. So be aware of those exceptions. Yep. Here's an example problem. Check for understanding. Identify the atom with the electron configuration argon 4s2 3d5. Okay, so pause the video, think about this, resume when you think you have an answer. And that answer is manganese. This is not one of the exceptions to worry about. This is the lowest energy configuration of manganese. So how do these electron configurations relate to the periodic table? We gave some names to groups in the periodic table before. And keep in mind that the periodic table is a way to arrange things that have similar chemical and physical properties, right? And we mentioned in this video already, things in the same group have the same valence electron configurations, meaning they react similarly, because these valence electrons, as we will see in chapter 7, are the key players in chemical reactions. Okay? So how does this affect the periodic table and the naming and now solidifying our understanding? Okay. Earlier in the semester, we said groups 1, 2, and then 13 through 18 are considered main group elements. Okay, so now we have a different definition. Instead of just memorizing it, a main group element is something where the last electron that was added went into an s or a p orbital. Those things we see on opposite sides of the periodic table, right? The s orbital on the left, those two, and the p subshell on the right, those 6. Okay. Transition metals we defined before. That's where the last electron went into a d orbital. That's our d block in the middle. And then lastly, our inner transition metals are where the last electron went into the f orbital, the f block. So these are things we learned earlier in the semester. That shouldn't be the first time you're hearing those, right? Main group transition metal and inner transition metal. Now we just have a new way of defining them. Okay. The last consideration we have for electron configurations is that of ions. Okay. And we've talked about ions since chapter 2, right? They're formed when atoms gain or lose electrons. A cation is something that's positively charged, and that can only be done by removing electrons. Remember, we can never change the number of protons. Yep. So the question is, what electrons do I pull off to make a cation? And if something is main group, so that last electron went into an S or a P, then whatever one was added last is the first one to come off, right? And you just take them off in reverse order. The only tricky part, if you have a cation, if that cation is a transition metal or an inner transition metal, it's actually the S electrons that are lost first. And then you get rid of the D and the F, which is why we commonly see +2 ions in the transition metals, in the inner transition metals, because they lose the 2 S electrons. Okay? But that's the tricky part here. Make sure that's on your radar. If you're making a cation, we have to lose electrons, right? If something is +3, for example, it has to lose 3 electrons. And for transition metals and inner transition metals, we always take the S electrons away first. Okay. Anions, which are negatively charged ions, are way easier because we just continue to add electrons, however many we need, right? If something is -2, it needs 2 extra electrons. So that's a piece of cake. Right? We just continue to add them like we would for the Aufbau principle. So this slide here has a lot of really good practice for you to work on before you jump into the sapling. It asks about the electron configuration of sodium, phosphorus, aluminum, and iron, now with some ions, okay, and samarium down here. Don't worry as much about E. Try A through D to figure out the electron configuration of 1, 2, 3 cations and 1 anion. Those answers are on the next two slides, and that'll bring us to the final section from chapter 6, which is where we talk about some element properties.